Hello everyone, this is Siddhartha Chaudhary from Indian Institute of Technology, Kharagpur. Today I am going to talk about our paper, A Minimalistic Perspective on Koblitz Curve Scalar Multiplication on FPGA Platforms. This paper has also been co-authored by Dr. Devapriya Basu Roy, who is a postdoctoral fellow in Technical University of Munich, and Professor Devdeep Mukhopadhyay of IIT Kharagpur. Let us start by introducing a brief description of our paper. Elliptic curve cryptography is an approach to public key cryptography which is popular due to its ability to provide the same level of security as RSA but with much smaller key size. But its complex arithmetic operation leads to difficulty in achieving a lightweight implementation. In this proposed architecture, we will be implementing a lightweight elliptic curve scalar multiplier on a FPGA platform. We have chosen a binary field curve, namely Koblitz curve, which provides excellent optimization opportunities. Arithmetic operation in characteristic 2 fields are easier to achieve because of the simplicity like carryless operations. For implementing the scalar multiplier, we will be using a one instruction set computing framework. Next, we will be discussing the design details of our proposed architecture. In the proposed work, we will be implementing the scalar multiplier over a NIST K163 curve. We will be employing two popular methodologies. First, a Montgomery lather technique. Second, a method proposed by Solinas where we will be using the non-adjacent form of the scalar. For the single instruction framework which we have chosen, we will be using ADDN as the appropriate instruction. Both the approaches will be implemented within the same framework without any additional cost of hardware. Both the approaches have their pros and cons. Montgomery has the advantage of having a lightweight point addition and point doubling formula, whereas there is no scope of reducing the length of the scalar. Whereas in case of Solinas, the point doubling is replaced by a low-cost Frobenius operation, and also the length of the scalar gets reduced by using non-adjacent form of the scalar. But point addition and point doubling formula are quite expensive in case of Solinas. Now, let us explain why the single instruction architecture. The first single instruction architecture coined as URIX was constructed by Madhavath and Paramath in 1988. Now, it can be evidently shown that instructions like ADDN can be used to construct Turing-complete processors. A single instruction framework can be used to construct extremely lightweight and efficient architectures. Now, the first elliptic curve scalar multiplier for prime curve was constructed in 2015 by Devapriya Basu Roy and et al. Using SBN instruction. In the proposed architecture, we have used ADDN instruction where ADDN is add and branch if negative for the implementation of the scalar multiplication. But we have actually faced more than a few challenges in the single instruction architecture. A standalone single instruction architecture cannot be used to design a complete elliptic curve scalar multiplier. Now, in order to comply with the computationally intensive scalar multiplication operation, we have integrated a dedicated right shifter, a dedicated field multiplier, and dedicated field squarer in the proposed architecture. Moreover, as we will be working with mostly characteristic 2 fields, both addition and subtraction are bitwise XOR operations. FPGA primitives such as DSPs will be of no use as they are only capable of performing integer operations. So in the proposed architecture, we have tweaked the integer DSPs to perform XOR and AND operations. Additionally, in the proposed architecture, we have used Lopez-the Hub projective coordinate system and Itosuzu inversion technique. Now, let us take a look into the details of the ADDN instruction. As we can see, the original ADDN instruction comprises of 3 operands A, B and C. First, we will add the values in address location A and B and store the result in address location A. And then we will check whether the value stored in address location A is less than 0 or not. If it is less than 0, the program pointer will jump to address location C, or else it will jump to the next instruction. But in the proposed architecture, we have actually modified the original ADDN instruction to comprise of actually 4 operands. As we can see, it comprises of C, A, B and D, where the result of the addition of the values in A and B are being stored in C, and if the result is less than 0 in C, the program pointer will jump to the specified address location or else to the next instruction. Now the ADDN instruction is modified to infuse pipelining into the proposed architecture. Now as you can see in the picture below, we have included two data memories instead of one so that we can achieve concurrent data reading and writing. Next we will demonstrate how are we able to read and write into the same data memory in the same clock cycle. We must mention a small fact that the data memories are configured as true dual port block RAMs. Now going into the details of the clock cycles, in clock cycle 1, data 1 and data 2 are being read from data memory 1 and data memory 2. In the second clock cycle, data 3 and data 4 are being read from data memory 1 and data memory 2, and consecutively the adder performs operation on data 1 and data 2. In the third clock cycle, data 5 and data 6 are being read from data memory 1 and data memory 2, and consecutively the output of the addition on data 1 and data 2 is being written onto data memory 1. Now let's get into the details of how we have implemented finite field XOR and AND operation using integer DSP adders. The first operation that we perform is a rewiring operation, where we take the operands A and B and then expand the length of A and B by including 0 at every alternative bit positions. Next, we perform two concurrent addition using DSP adders between the lower half of A and the lower half of B and the upper half of A and the upper half of B. Then we combine the even position bits of out1 with the even position bits of out2 and the odd position bits of out1 with the odd position bits of out2, which actually signifies the sum bit and the carry bit of the integer additions. So out3 is actually A XOR B and out4 is actually A and B. Now let's demonstrate this with a small example. Now as you can see in the example, we have expanded the length of A and B by infusing zeros at every alternative bit positions. Now we add the lower halves and the upper halves of A and B using DSP adders. Now after obtaining out1 and out2 in this step, we will mix the bits of out1 and out2 to get out4 and out3. Now as we can see in this step, we have obtained the sum bit and the carry bit, and we have obtained A XOR B and A and B. For the final output, based on the select line of the marks, that is XOR and CON, we obtain whether A XOR B or A and B. So we were finally able to use hard IPs like DSPs to obtain the value of A XOR B and A and B. Now we will take a look into the most important component of a scalar multiplier, that is a field multiplier. For our implementation, we have used comma multiplication algorithm for implementing field multiplication. This slide depicts the basic architecture of the field multiplier. From the comma multiplication algorithm, we can see that we require a basic field multiplier. For our convenience, we did choose the word size for the comma multiplication algorithm to be 48 bits. We have implemented few basic pipelining techniques within the multiplier architecture. The control unit handles the scheduling of the algorithm, and the UV reg in the figure depicts the UV register within the comma multiplication algorithm. We have implemented the field multiplier to achieve a low area architecture and a high area architecture. As you can see from the picture below, the low area architecture requires 112 clock cycles to obtain a field multiplication output, whereas the high area architecture requires only 32 clock cycles to obtain a field multiplication output. Now, there is a subtle difference between the two architectures. As you can see from the low area architecture, it employs a sequential Karatsuba multiplier which requires 5 clock cycles to give one output, whereas the high area architecture employs a combinational Karatsuba block which gives output in 1 clock cycle. Now this creates a difference in the overall latency of both the multipliers. We have implemented both the multipliers so that we may obtain a design with the best area time product. Now we will give a small example on actually how we have coded the instructions. Now this is a lazy reduction algorithm that is actually employed to reduce the scalar length in case of Solinus's method. Now analyzing the code snippet, we can see that we need 4 basic types of operation: a integer addition, a XOR operation, an AND operation, and a right shift operation. As we did already mention earlier, we are having a dedicated right shifter integrated into the ADDN processor. Now other than the right shift operation, The other operations were performed using a basic ADDN instruction structure. Now, using this unified instruction structure, we were able to achieve the desired output of this code snippet. Now, let us share some few details of actually how we relate the lines of the algorithm with our instruction set. As we can see, the highlighted line in the algorithm depicts if D0 is odd, then assign 1 to U or else assign 0 to U. Similarly, in our instruction set, what we did is we did AND D0 with 1 to find out what is the value of the LSB and did assign the value of the LSB to U. Next, in order to decrement the value of D0 by 1, what we did is we did find the negative value of 1 and add it with D0. Now, as you can see, few steps of the algorithm requires the value of D0 by 2. Now, in order to find the value of D0 by 2, we did perform a right shift operation on D0. In this manner, we did code the whole scalar multiplication algorithm using our unified instruction set. Now, we will be looking into the working of the entire scalar multiplier architecture. Now, as you can see, the processor architecture consists of the basic building blocks, the instruction memory, a data memory, and an arithmetic and logic unit. The arithmetic and logic unit consists of a field multiplier, basic DSP adder blocks, and a field squarer. The instruction memory consists of instruction that is having a basic layout as depicted in the instruction layout image. Now, going into the operating steps of how the scalar multiplier processor works, the instructions are being fetched from the instruction memory based on the output of the program counter. Now, based on the instruction, the data is being read or written into the data memory based on whatever flag is being activated in the instruction and based on the memory address that is being specified in the instruction. Now, whatever data is being read from the data memory, operations are performed on those data by the arithmetic and logic unit. Now, based on whichever ALU unit is needed to be activated, the DIN select module selects the data based on the DIN select input and delivers the output of the ALU unit to the data memory. Now, let us take a look into the implementation details of the entire processor. We have implemented the entire design in a modern low-end Xilinx board RTX 7. From the resource utilization table, we can see that we have used a very small portion of the resources available on an RTX 7 board, thus leaving space for the other components of our SoC to be integrated. Now, taking a look into the comparison table, we can say that our proposed design consumes very low resources and delivers output within a reasonable latency, thus delivering a competitive area time product. Now, taking a further look into 4 of our designs, it consists of 2 low area designs and 2 high area designs based on 2 approaches, the Montgomery ladder technique and the method proposed by Solinus. We were able to conclude that a design that uses the Montgomery ladder technique along with the low area architecture multiplier was able to deliver the most efficient area time product. Now, on a concluding note, we want to say that we were able to achieve a lightweight hardware framework for implementing ECC scalar multiplier on Koblitz curve with a competitive area time product and an architecture which supports both the method proposed by Solinus and Montgomery ladder technique. Thank you for your time.